Welcome to the final lesson in this module, which takes a step back and evaluates all the concurrency and parallelism mechanisms in Java that we've explored in the previous lessons. In this lesson, you'll learn which Java mechanisms to understand and apply based on the context in which they're being considered. As we've seen, Java's concurrency and parallelism mechanisms span multiple layers in a classic software stack, going from the hardware, the operating system kernel, low-level system libraries, the Java execution environment, such as the JVM or the Android runtime, the concurrency and parallelism frameworks, including Java threads and synchronizers, additional application frameworks, all the way up to applications. Choosing the best mechanisms depends on various factors, in particular, which layer or layers in the stack you're actually trying to develop for. Developers of low-level classes and/or performance-sensitive apps, such as perhaps gaming apps, may prefer to use the shared object mechanisms we talked about. These are basically the synchronizers that you would find in Java util concurrent locks or Java util concurrent atomic packages and so on and so forth. So if that's where you're focusing, if you're trying to build applications that need to be very optimized for the underlying hardware and the application requirements in terms of latency or throughput and so on, you might want to consider these shared object synchronizers. The benefits of the shared object approach is it's efficient and lightweight because you're really programming close to the metal. The downside is that that type of programming with those lower level mechanisms tends to be somewhat tedious and error prone. And therefore, the shared object synchronizers are often best used by people building infrastructure using Java rather than people developing higher level apps where you might want to focus more on productivity and ease of development rather than raw performance. Developers of frameworks, which are things that would sit on top of the lower level execution environment and system libraries and so on, might want to consider using Java's message passing mechanisms, things like the array blocking queue or the link blocking queue and so on. Examples of these kinds of frameworks that exist in popular platforms today would be things like the Android Hammer messages and runnable framework, or the so-called Hammer framework, as well as the Java executor frameworks like the Java executor service and executor completion service frameworks. And these frameworks tend to use a lot of message passing internally to move information, typically some kind of task or some kind of runnable, from one threading context to another. The benefits of using message passing versus, say, shared objects is that they're flexible and they're decoupled because you don't have to worry about locking. You're typically not having threads access shared mutable data directly, but instead they're passing messages by some thread safe or synchronized message queue. The downside is that there's a bit more time and space overhead by doing this kind of coordination and interaction rather than using the shared objects directly. And that's because there can be higher levels of context switching, higher levels of synchronization, more data movement overhead, which ends up perturbing instruction and data caches, and so on and so forth. So message passing is a good paradigm for framework developers, but won't necessarily get you the raw performance that using those shared object synchronizers may, that we talked about earlier. People building apps might want to focus on the higher level frameworks that are now available with Java. And this, of course, includes the various parallelism frameworks we talked about, like Java parallel streams. It includes the asynchronous parallel frameworks, such as completable futures, as well as these cool reactive streams frameworks, such as RxJava and Project Reactor. And these frameworks really raise the level of abstraction quite a bit so that you're programming at a higher level model, and the framework implementations are doing an awful lot more of the work under the hood to manage the concurrency and manage the parallelism, and any synchronization or any kinds of visibility and atomicity constraints and properties are also automatically handled by those frameworks. The nice part about using these higher level concurrency and parallelism frameworks is they tend to increase productivity, they tend to increase robustness, and of course, if you're programming them effectively on modern multi-core processors, and you've got nicely, embarrassingly parallel application requirements at your disposal, they also tend to be very efficient. The downside is that because they're at a higher level of abstraction, you might run across more time and space overhead relative to using the lowest level mechanisms like threads and reentrant lock or other common mechanisms like compare and swap. And to some extent, you're also a bit at the mercy of the programming model that these frameworks embody or define. So they can perhaps be a little bit overly prescriptive. For example, divide and conquer style programs work very well with Java parallel streams. But if you don't have a divide and conquer model, then that may not be the right choice for you. So obviously, if you're really trying to capture that elusive full stack developer status, you would want to be able to understand all the mechanisms that we've covered here, ranging from the low-level shared objects to the sort of meso or middle-level message passing mechanisms up to the more advanced frameworks for parallelism support, especially things like parallel streams, RxJava, reactive streams, completable futures, and so on and so forth. But the main point here is to realize that, like the people say in, I think it's Australia, there are different horses for different courses. So we want to be able to pick the right framework or the right mechanisms based on the requirements and the environment, both hardware and software, in which our applications or our software is going to be running. So hopefully you have a little bit better idea now of how to pick and choose between these different models. And I also hope that you get a chance to try to learn them all and see which ones you like to use best for what you're trying to do. Regardless of which Java mechanisms and frameworks and so on that you select, you need to be prepared to master the accidental and inherent complexities of concurrent and parallel programming. And all these mechanisms and frameworks help you in that case, in that capacity, but there's still additional work to do. This particular meme has always struck me as being funny. It says, whoever said the definition of insanity is doing the same thing over and over again, but expecting different results, wasn't debugging concurrency issues. And that is so true. So you'll always end up having to wrestle with some of these issues, especially as your systems get more complicated and your requirements get more complicated and the number of processors you have at your disposal gets larger and so on. But hopefully now you have a better idea of how to guide yourself through the different paths in this very fascinating garden of concurrency and parallelism mechanisms in Java. So that's the end of our evaluation of concurrency and parallelism mechanisms in Java, and I hope you enjoyed this module in the course.